Ever wondered how your phone or computer handles billions of operations every second without crashing? It's all about timing, like a symphony where every note has to hit just right. Today, we're diving into a breakthrough study that's rewriting the rules of digital circuit analysis, using a clever tool called answer set programming to make sure your devices run faster, smoother, and with fewer glitches. Imagine you're designing a circuit, like a complex maze of roads. Every path through this maze has a different speed limit, and you need to find the slowest route to ensure nothing breaks. That's what timing analysis does, identifying the longest signal path to prevent delays. But here's the twist. Traditional methods often miss hidden hazards, like signals that glitch or interfere. This research, it's about catching those sneaky issues with a new approach. The team compared two encoding strategies in a system called ASP, answer set programming, which is like a super smart puzzle solver for circuits. Their data shows a clear winner. The advanced encoding isn't just faster, it's a game changer. For example, take the notorious C6288 circuit, a 16x16 multiplier with so many paths. It's like solving a maze with trillions of dead ends. The old method took 10 hours to analyze, the new one less than 4. And for B14, a massive processor subset, the advanced method cut memory use from 12 GB to under 2 GB. That's like shrinking a library to a single book. But why does this matter? Well, modern chips have billions of transistors. If a timing flaw slips through, it could cause everything from a frozen screen to a car's brakes failing. The advanced encoding doesn't just find the longest path, it accounts for hazards, like signals that flip at the wrong moment. It's like adding a traffic cop to your maze, not just measuring speed. This isn't just about speed. The researchers also looked at how others tackled timing analysis. Some methods shortcut by focusing on specific parts of a circuit, but that's like checking only one lane of a highway. The ASP approach is more thorough, even if it takes longer. And while machine learning or simulation tools offer quick guesses, they're not 100% accurate. Think of them as GPS directions that occasionally send you off a cliff. So what's next? The team wants to combine ASP with new math tools to handle even trickier circuits. For now, this work is a giant leap for hardware design, ensuring our tech stays reliable as it gets more complex. The next time you use your device, remember, behind the scenes, algorithms like these are working overtime to keep everything running smoothly. But there's another layer to this puzzle. Imagine a digital circuit as a busy highway. Every task it processes is like a car moving through traffic. But what if the circuit guesses how long a task will take and gets it wrong? Just like a wrong turn can cause a traffic jam, these errors slow things down or crash the system. That's timing speculation, the circuit's best guess but not always a correct one. Enter input vector profiling, a technique that acts like a real-time traffic app for circuits. Instead of guessing, it analyzes patterns in the data flowing through the system, like tracking road conditions to suggest the fastest route. By spotting these patterns, the circuit adjusts its timing on the fly, avoiding delays and errors. The result? Faster, smoother performance in everything from your smartphone to the sensors in a self-driving car. This isn't just about speed, it's about reliability. The first paper we talked about gave us smarter decision-making systems. This one ensures those systems don't hit roadblocks. Together, they show how logic, prediction, and error correction are the quiet heroes behind the tech we take for granted. Next time you're amazed by a robot's precision or your phone's responsiveness, remember, it's built on research like this. Science isn't just in labs, it's in the heartbeat of the technology shaping our world. Stay curious, and let's keep uncovering the stories behind the screens.